I'm moving in today.
Intimacy is all I ever wanted. For someone to keep having till the day
Alright, so I just got to my apartment. I'm moving in West Kensington for the semester with Audrey and Dorothy, who are also doing the RCM program. There's good news and bad news. The good news is that I get my own room and my own bathroom, but there's a couple pieces of bad news. First of all, it's on like the 4th floor and there's no AC. It's currently 86 degrees in here and I'm pretty sure outside it's like 70. So I'll give you guys a tour and then I will go put on my stuff. Let's go. All right, so after we come in, Audrey and Dorothy's room is on the left. All right, straight ahead, we have the kitchen, coffee table, dinner table, and a couch. This is a nice little living room. This is my bathroom here. And then over here is gonna be my bedroom and my little closet. So, not a bad living situation. It's just really hot, so hopefully it gets to winter kind of soon.
too quickly, you'll fall out of my reach. I'm falling over now.
Well, I'm pretty much finished unpacking. I didn't really bring that much stuff, so it wasn't that bad. Audrey and Dorothy are here, so we're probably gonna go look for some fans and then go eat lunch or something. This is worse than Rocky and Maddie. But yeah, this is the room.
Think that we have got what it takes to last more than a minute, and you fell right past me. Is it just another thing? I really thought it was meant to be. I'm like a rowboat swept out to sea, hoping that someone's looking for me. The water cuts me like a blade.
Fan secured. Alright, we just got back from like fan hunting and getting our SIM cards. I got a UK SIM card, so that I actually have data. Now I'm gonna meet with Daniel to talk about planning Opus initiations because that's coming up soon. I'm done practicing. I'm so tired. I'm going to go shower and then probably watch some Netflix. I have a tiny ass fan. That's it. That's all I have to survive this 90-degree weather, or 31 degrees Celsius. Sorry. Good night. But yeah, I moved in. Apartment's not too bad. It's just too hot. But you know, in 2 weeks it'll be great because it'll be cool and whatever. So. Okay, so even though I'm really behind on this, I am not going to leave out the MCAT stuff in this video, but I know I've been really behind, so I guess I'll do my best to keep it going, but like it's getting a lot harder. But yeah, right now I'm going to go through chapters 4, 5, 6, and 7 of the Kaplan Jenkins book. I'm gonna do my best to limit myself to like 1 to 1.5 minutes per chapter. Okay, so here we go. So chapter 4 is compounds and stoichiometry. So there's a couple definitions to go over. First of all is molecular weight, which is just the sum of all the atomic weights. This is measured in AMU per molecule. Then there's molar mass, which is the mass per mole of molecule. And they should be the same number. Then there's equivalent weight, which is molar mass divided by N. And N is like the number of particles of interest. So basically it's like the mass of a compound that gives you 1 mole of something that you want, right? Normality is going to be molarity times N. So for example, 1 N of HCl is going to be 1 mole of hydrogen ions because there's 1 hydrogen ion per molecule of HCl, so 1 N becomes 1 M. Then there's a bunch of different types of chemical reactions, and they're listed here. And then there's a bunch of like polyatomic ions, which I put like a little chart here. Okay, when ions are in solute, they let solutions carry current, which makes them called electrolytes. And a strong electrolyte is basically like NaCl where it completely dissolves. Chapter 5 is kinetics. And basically, there's a bunch of like reaction mechanisms, which is basically how a reaction proceeds. So instead of just A plus B goes to 2C, there's different steps like here. And when reactions happen, there's like this collision theory, which is basically that like molecules have to collide with each other in a certain way in a very specific manner so that they actually like go to the transition state and react to form the new molecule. And the rate of this reaction is proportional to how many collisions per second there are. And this gives us the Arrhenius equation, which is here. Factors that affect reaction rate are the concentration of reactions. Usually if you increase the concentration, then the reaction goes faster. If you increase the temperature, it also goes faster. Then there's like medium and catalysts. So for medium, if you have polar solvents, then the bonds are going to be more polarized, which means that they're more further apart, and so they're weaker, and so it's a faster reaction. Then a big thing is like reaction rates. So here's kind of just like a toy example of what the rate would look like for this reaction. And if you have like rate is K equals like A to the X, B to the Y, then the reaction order is going to be X plus Y. Then there's like 3 different reaction orders, or main reaction orders. There's 0 order, which basically means that rate is independent of the concentration of the reactant. And so here's an example of the graph. The concentration of A just decreases over time. For first order, the rate is going to be proportional to 1 reactant. So it's going to be K equals like A to the first power. And an example is like radioactive decay. And basically, it's going to be, the graph is going to be linear for time to ln of the concentration of A. For second order, it's going to be like K times A to the first, B to the first, or A squared, B to the 0, or etc. And basically this is linear for like time compared to the reciprocal of the concentration. And so a way to remember this is like acronym is CLEAR. So for 0 order, it's constant on the y-axis. For first order, it's going to be ln, and for second order, it's going to be reciprocal. Okay, so chapter 6 is equilibrium. For a lot of reactions, they're like reversible, and so it's like reactants go to products and products go back to reactants. And equilibrium happens when the concentrations of the reactants and the products are constant. It doesn't mean that they're exactly equal. So basically, for this reaction, basically at equilibrium, the law of mass action states that K at equilibrium is going to be equal to this. Where pure solids and liquids don't count towards this because they don't really change in this reaction fast enough to matter. For reactions not in equilibrium, instead of K, we use something called Q, which is basically the same formula as before. But basically, if your K at equilibrium is greater than your Q, then you're going to be increasing the forward reaction because basically you don't have enough products. And if it's vice versa, then you go the other way because you have too many products. Okay, in general, for some equilibrium calculation problems, some things to remember is that if you have a large KEQ, then that means that your numerator is much bigger, which means that you have a lot more products than reactants, which means that the reaction basically goes to completion. If you have small KEQ, then it really favors the reactants. And so in cases like this, basically you can just assume that if you use like X amount of the reactants, you can just ignore it because it's so reactant favored that this little bit is negligible. And so here's an example of like a possible calculation you can do to find how much of a certain reactant is used. Another thing to know about equilibrium is like Le Chatelier's principle, which is basically that like when things go out of equilibrium, the reaction just moves in the direction that would put it back to equilibrium. So for example, like if you increase the concentration of reactants, it's just gonna increase forward reaction so that the products are more, and so it's equilibrium again. So okay, so when the system's compressed, the volume decreases, and so the pressure increases, and so to restore equilibrium, you want to decrease the total pressure. Basically, there's this like thing where the more moles you have, the more pressure there is for the whole system, and so that means that when you increase the pressure, then your reaction is going to favor the side with less moles, so that overall there's less pressure, and that brings it back to equilibrium. For heat, you basically treat it as like a product or reactant, so like plus delta H on either the reactant or the product side, and you do the same thing. And then there's like kinetic versus thermodynamic products. So basically the kinetic product is just the one that forms faster because there's less energy that you need to actually get this product to happen. And so this works at lower temperatures, but at higher temperatures, the thermodynamic product is favored because since you have the energy that you need, it just forms a more stable product. Thermochem is a lot of like formulas, and it's a lot of the concepts are kind of really hard to like summarize in a short way. So I think I'm just gonna like leave my notes here. I don't know. It's actually really hard to like make a short-ish video where I try to explain things. So like I don't know. I think just like a very quick summary is like the best I got. But the notes is I'll leave the notes in general like in the video, and hopefully they help. But I'm gonna try to upload a vlog of when I went to Amsterdam the past weekend as soon as possible, and I'm going to Vienna as well, and so I'll try to record that and do that all in a timely manner. But yeah.
Till the day I don't float.